Well, it's a great pleasure to be here. Thank you for coming. Last time I was in Irvine was almost 25 years ago. I had just gotten my PhD and was looking around at various departments, and I remember being very impressed with what was going on here. And it's obviously worked out really well in terms of the building of the various faculties and departments and so on. And also I feel I share a lot with Irvine in terms of the sort of intellectual, technical legacy in terms of early work in software architecture, programming environments, and so on. So there's a lot of correspondences here. So it's really nice to be here, and of course the weather is great to be here again. Today I want to talk about something that's a fairly new area for me, although in some ways it goes way back to the roots of my own research, which really asks the question, how do we provide tools for software architects to do what they want to do? And this looks at the same kind of issue, but tries to look at a different collection of people who might benefit from some of those techniques that we've been working on for 2 decades now. So let me just give away the whole talk here, and you can decide if you want to leave. In a nutshell, what we see today is commonplace that technology and computation is pervading everyone's life, but it does so in very different ways for different people. So there's a certain kinds of people that depend fundamentally on computation to do what they do, but they're not programmers. They're people like physicists or medical researchers or other e-science people, intelligence analysts, and so on, who are going to use computation, and often in innovative ways. They're not going to be able to necessarily go buy exactly what they need off the shelf and use it. They need somehow to tailor that computation to what they do. But today, they are poorly served by what's out there. In fact, in many cases, they have to become programmers. They have to immerse themselves in all kinds of details they really don't want to worry about, or hire people to do it who tend to do it very badly. But the insight here, and what I hope to convince you of, is that when you look at what they do, is very, very similar to what architects do in the more traditional sort of software engineering, software development fields. That is to say, they're concerned with putting together systems, largely from components that exist. They're concerned with the nature of the compositions, the systemic properties of it. They're concerned with typically domain-specific specializations that give them some leverage in that domain, and so on. And we can see parallels between what's gone on in architecture and what they need. And then the hypothesis here that I'm exploring is, can we then take the things, the tools, the techniques that we develop for architects, where can we move those over to help this kind of user? And where are the problems? Where is it that we get into trouble? Where is our intuition break down when we try to do that? What's needed in addition? And then perhaps coming around full circle, what does that tell us about software architecting tools for software development? So the kinds of things that I'm going to talk about that I want to draw on from software architecture, and by the way, if you don't know about software architecture, I'll say a little bit about it, are the idea of picking abstractions that are appropriate to a user's domain. Second, being able to think about computation and compositions in a way that gives them feedback and guidance so that they have some idea what properties their system will have, and also gives a certain amount of execution support for those compositions. The final thing I want to come back to, which is in this particular world, and I think many worlds, what we find is that the ecosystem in which the technology lives is actually fairly complex. And in order to actually have successful transition of this technology into the world of what I'll call end-user architecting, requires a fairly deep understanding of the ecosystem context. And I'll be explicit about what I mean by that. Okay, so the background here is, as I said, when you start looking around, you see that there's this interesting class of people who depend on technology, but it's not about So they'd execute programs, someone had to write the code, and they're going to use that, but that's not their primary job function. Their primary job function is to look for disease pathways in brains through looking at various sorts of MRI images, or do intelligence analysis to figure out patterns of drug gang activity in Los Angeles, or doing things like that where they depend on computation, they depend often on big data, and they're going to put things together in novel ways. What they need today is not what they need tomorrow, but they don't want to necessarily become programmers. And so they would like to assemble these computations. Often the computations might be built by different companies or different organizations. The data may come from a variety of sources. And to compose these into systems actually turns out to be a bit of a headache, often because when they try to put the various parts together, they just don't work. So let me give you some examples of the kinds of fields I'm talking about. Neuroscience is certainly one of them, and it's one of the areas we've been working with. In Portugal, actually, there's a very large brain imaging network community, and they are sort of a repository of brain image information for Europe, and a lot of people come there to study brain imaging and do medical research in that. Dynamic network analysis, we have someone in our department, Kathleen Carley, who's kind of an expert in dynamic networks, which by that they mean essentially social networks on steroids. They have very complex nodes and relations that involve people, places, times, and support fairly sophisticated analysis of social, cultural, anthropological data. E-science, there are lots and lots of aspects of e-science. Perhaps everywhere in science, people are depending on computation, from astronomy to physics to biology and so on. Bioinformatics is another obvious one. But even in the sort of business process management world, which is more familiar to many of us, people have to put together services and create support for business process within the organization. Some more emerging ones, I think, are things like smart buildings, smart energy in homes, building management, where increasingly we have data, about energy use of the appliances and things like that. We'd like to link all this together into smart computations that help reduce energy footprint and so on. Personal medicine, when we think about individuals who want to take advantage not just of information that their doctors happen to have in patient medical records, but the wealth of other health-related information out on the internet. How do you put that information together and extract out the parts that are relevant to you? Well, you can imagine doing that through compositions that find the right information, select the right features, and provide the information you're looking for. Digital audio systems, these have been out for a long time, but systems that let you compose various kinds of virtual components to do music synthesis or other kinds of audio things. So that's just a few domains to give you the idea here. What do they have in common? Well, they all involve some serious computation. They all involve composition. They all involve a certain amount of exploratory development. So when you start to put things together, you as the user of this don't necessarily know exactly what parts you need. You may not know exactly what you're looking for, and so you're going to be playing around with this. And you often care about certain quality attributes. So for example, in the personal medicine world, you might be nervous about privacy concerns. If I expose my information about my personal health to some program that's going to transform it and maybe give me some interesting insight, can I be sure that that program doesn't ship that over to some company that's going to try to sell me drugs or something? Okay? So there are lots of concerns, from security to reliability to performance, that are systemic properties of the computations that even we as users of the technology will care about. Okay, so what's the problem? The problem is actually, even though there's a potential today for taking advantage of this information, for using it, to do it often requires a lot of knowledge about low-level details. I'll give some examples in a minute, but in the domains we've looked at, often there are hundreds of parameters that you may have to specify. File systems that you have to understand to know where everything lives. Various kinds of constraints on operating sequences, and so on and so forth. That when you get down to actually saying, okay, how do I make these off-the-shelf components work together, you end up having to immerse yourself in an awful lot of very cumbersome low-level detail. And so, people who have to do this often just hire programmers to do this, and then it works, but it's expensive and it often doesn't give the results you want. There's a conceptual mismatch. So when I think, let's say I'm a brain imaging person, and I think about what do I want to do to transform these images into something that's useful to me, the kind of thing I want to do is to say, well, I need to remove the image noise from a sequence of slices, but I can't do that. I have to figure out, which program will do that for me, and what specific set of parameters do I give it in order to get it to do that. Once you start even finding and putting these things together, you have very little support for error detection and fixing it. So if you plug the output of this tool that this company built into the input of a tool for this company, chances are they're not going to work together. And so now you have to worry about how do I convert the output of this to the input of that, and now you're off looking for yet another tool, and the whole issue becomes really a nightmare once you start getting dozens of these components that have to work together. And finally, in many of these domains, there's a community of users that would like to benefit from what others do. So if you're a brain imaging researcher and you come up with some very cool analysis that you want to, that you've discovered works really well to extract certain kinds of information, you'd like to be able to ship that over to your colleague and say, hey, run this on your data and tell me what you think. But today, packaging that up and reusing that at all is really impossible practically, because this stuff is all wired into fairly crufty, special purpose compositions that don't really allow anyone to move it from one place to another. So those are all symptoms of the fact that there's a mismatch now between what people really need out of computation and what they get, today, given the things that are around us. So again, I'll give you a couple more examples here to kind of deepen the understanding a little bit about what's missing. So brain imaging, as I said, we're working with this this research organization in Portugal, and they have these really large repositories of brain imaging data. I don't actually understand this field very well, but I know a little bit about it. I know that when I look at the kinds of scripts that they create to do something interesting, it's unbelievably complicated. I have no idea how they do it, and I'll show you what I mean in a minute. But there are dozens, if not hundreds, of processing tools that take these images and do things to them to extract certain features or correlate certain behaviors over time, or even reconcile sort of different angle orientations and so on. And they have to do all this if they want to use the data. So here's an example. So in the first box there's a slice that's been taken and an image. In order to use it, they're going to have to do a certain amount of alignment to get it facing the right way, and then they're going to extract out certain features of it to produce the parts that they want, and then some other kind of process to get it into yet another form. And they're going to do this many hundreds of times over a series of 1,000 of these slices, and then pipe that onto some other tool that's going to come up with some interesting analysis. Okay, so that's an example. Now, even the simple one here, what needs to go on? Well, first of all, we got multiple programs, and each program that we pick could very well have been built by a different organization. Each of those programs typically has a dozen to 100 parameters that affect exactly how it does its job. And this is kind of what it looks like. You end up with these ridiculously long scripts where if you take a little portion of it, this is the sort of portion of that script for one particular step in an analysis. Recognize that these analyses are often a dozen to 20 or so steps that go on. So you can imagine that just getting this right, getting those parameters sorted out, knowing which tools to use and so on, is really a bit of a nightmare. Here's another example. This is, as I said, we were working with people who develop these tools for network extraction, and often what happens is you'll get inputs of unstructured text like web pages and blogs and SMS messages, and they'll process that through various natural language tools that extract key features, people, places, names, relationships, and so on. And then what they do is they create networks which they can do a lot of processing on, including simulation, looking for key entities, mapping to geospatial renditions, and so on. A fairly sophisticated set of tools there. And some of the places where you see this and used actually are sponsors for doing this were people in the HSCB, Human Socio-cognitive Behavior Program, and these are the ones that are trying to help out in Afghanistan, where increasingly when you send troops out there, you don't want them to start shooting people, you want them to sort of make friends with the elders in the village. Well, in order to do that, they have to understand the social structures of the village, who's important, who to interact with. Where do you get that information? A lot of it comes from these tools that help understand, what are the socio and cultural and religious structures in a country. Other places where this is being used are criminal activity monitoring in metropolitan areas, so drug enforcement uses these a lot. People in business do this for business intelligence, trying to understand our competitors and who's buying what and supply chains, and so on. People have looked at this for how best do I communicate policy changes in cities so that information will propagate out quickly. And lots of different kinds of tools, all the way from sort of natural language understanding to network analysis to simulation and actually various kinds of gaming tools. So an example of where this is used and where some of the problems occur. So in Haiti there was an earthquake in 2010, and a lot of humanitarian effort was poured into that. And there was a fair amount of information that came out of that in the form of emails and public domain news sources and all kinds of things like that. If you wanted to understand that phenomenon, you could take all that, sort of extract out things over time, try to understand what activities were going on in Haiti, with the idea, hopefully, of understanding how to do better disaster relief for other kinds of events. So a lot of people worked on this. This was a data set that many people in this field took as a kind of a challenge problem. And they would create these networks from them, and they try to answer questions like, what organizations were involved in the relief effort and how? When did the emphasis shift from rescue and the sort of keeping people alive to finding fresh water? How did the government, NGO, and also foreign government relationships and organizations work together? So all those kinds of questions are useful. And the way it works is the inputs are things like this. So this is just a bunch of text that's actually been processed a little bit. If you could look at this closely, you'd see there's certain words that are X'd out. Those are sort of noise words. And out of that, you generate a graph that looks like this. Often it's a very complicated graph, so many nodes and edges that you can't see the forest through the trees. And so then what you have to do is to take that and start extracting out information like key entities and so on. And there's some fairly sophisticated tools to do that. But ultimately, hopefully what you get is some kind of report that distills this all down into something that's of interest to you, and then can possibly be plotted in some kind of visual form that might help relate that to some geographical locations. Okay, so those are the kinds of tools you see, and this is a simulation that was run on some data. Okay, so these are all produced today by various sorts of tools that people have created that tend to be fairly large, monolithic things that take 6 months to a year to figure out how to use. And they're all done in largely stovepiped way, meaning that, if you know how to use AutoMap over there, it doesn't help you at all in terms of using Aura, and in fact, if you want to take the output of AutoMap, it may be even difficult to get it to Aura because someone else built that. In this case, that's not true because CMU happened to build these tools, but if you look at the broad spectrum of tools that are out there, that's often the case. Now, you might say, okay, well, one thing we could certainly do here is let's imagine that we want to make all this stuff available. Let's stick it out in a service-oriented architecture. In other words, let's take all of these tools and some data. Let's wrap it up in such a way that it's out there in some form, and that we can get at it through standard interfaces and coordinate all this stuff in what's now fairly familiar technology. So that seems like a very appealing way to go, in part because in the service-oriented architecture world, it's already dealt with this problem of heterogeneity, of distribution, of standard interface definitions, of protocols, REST and SOAP and so on, that we can use to hook things together. So you might think, well, great, that should solve the problem. It doesn't, though. When you look at, what does it take to write down a composition of, let's say, 4 logical processing steps, where each step is of the sort I showed you earlier, you end up with a VBL script that's just totally incomprehensible. You take any part of this, and it's this ridiculous set of very low-level commands that an orchestration engine will understand and will get the job done. But as you can imagine, creating this is a little like programming an assembly language again. So this is obviously not something that a brain imaging scientist is going to be able to do out of the box, or a sociocultural analyst. And so once again, people are going to have to hire programmers and work on this fairly low-level, grungy stuff. And even then, it's tricky to get it right. There's all kinds of issues with timeouts, how you deal with error handling, and so on and so forth. So something like SOA, on the surface of it, might seem like it's a great idea from a technology perspective, but we still have the big problem, which is, how do we bridge the gap between the technology and the people that really want to use it? Third example, in somewhat shorter detail here, another kind of emerging application of this concept is something called the Ozone Widget Framework, which is a kind of pub-sub form of integration. And what you do is you have a set of widgets that do various kinds of processing of information, and you hook them together over pub-sub channels. And these sort of are in the form of things like apps, but sort of for the intelligence domain. And you can hook these things together, and then you get this sort of dashboard here with these various sorts of interactive apps that are sort of communicating with each other. And the apps themselves run on various sorts of hosts off there. So once again, similar to the SOA story, you do have a kind of an execution basis where all these things can run, and a fairly nice front end. But when you start looking under the hood, you discover once again, to make this all work, there are a bunch of sort of complicated scripts that have to have all the right connections happening and the right messages going. And in general, again, you have to kind of immerse yourself in the low-level details of how these things are implemented and how all the glue works. Okay, enough examples. Let's talk about now what's needed. So I think, when we say, okay, what would represent a good solution here? So one is some kind of composition platform that's probably fairly domain specific, that people could use to grab the components they need, put them together without a whole lot of programming, and be able to do that in a way that sort of matches their intuition about what's going on. Of course, that's going to be different for a brain imager than for someone working in the intelligence analysis field. So we need to have a way to come up with fairly domain-specific composition environments or tools. And finally, we need to give them some help, a variety of help. First of all, they need to be able to find the various components. They need to be able to put them together. They need to be able to execute them. They need to be able to debug them. They need to be able to perhaps analyze them for things like, does this have the right security? Does it satisfy some security policies about information flow through these various tools? That's what we would like, and you can imagine that someone in this domain would really be thrilled if you could hand them one of these. Now, it turns out, actually, a number of these have been created, and if you look around, you'll discover that many communities have gone off and through a large amount of effort created exactly this kind of thing. So there are a number of them out there like Galaxy and others, that people have said, well, we have a big enough community, we have funding to do this, we'll go off and we'll hand create one of these specialized environments for our community and do that. But this is done at very high cost and over usually a very long period, and it's not transferable. So if you have one of these, it's particularly good, let's say for astronomy, it's not necessarily going to transfer at all over to brain imaging, okay? So you end up with a situation where we have actually good examples of these sort of end user composition environments that are nicely done for their community, but having been built at high expense. But anyway, the general insight here is that when we look at these kinds of features that we'd like, it's very similar to software architecture. The notion of composition, the notion of something that might be domain specific, with support for that, the notion of integrating execution with design, the notion of analyzing systems for specific kinds of qualities that we care about. So I know a lot of you know a lot about architecture here, but some of you may not. So let me just step back and say a little bit about what I mean by that and what I think is relevant for understanding what we did and perhaps more generally how architecture relates to this problem. Okay, so what is software architecture? Well, architecture emerged, I think, by recognition that a lot of the important design decisions that were made early on by people who figured out at a fairly high level of abstraction what the parts would be and how they would fit together. And those design decisions were often captured in the sort of familiar looking box and line diagrams that we see that accompany many system descriptions. And although those were fairly informal, they conveyed a lot of important information about how the designers thought about the system and what kinds of properties that they were hoping it would have, what kinds of constraints they might be imposing on how it fits together. So architecture represents a kind of modeling approach in which a certain kind of high-level representation is used to think about system design. And so in some sense, it breaks down the problem of getting from requirements to implementations, provides a sort of a middle layer where the architecture becomes a way to think through key design decisions, leaving the more detailed ones to later, typically where you implement. So there are lots of definitions of architecture. I don't think I'm going to go through this, but most of them have some notion of properties of interest and reasoning about the system and selection of structures. In the broad scope of things, architecture emerged in the sense of kind of being recognized by the software engineering community in the 90s and essentially was building on insight, I think, into what practitioners were already doing, but tried to make it somewhat more rigorous and well-defined as to what should be done as an architect, and then also started to provide tools to help out. So architecture became, I think, relatively well recognized and somewhat understood in the 90s, and of course lots and lots of things have followed since then, many of which are not architecture specifically, but build on those concepts. So certain kinds of model-based design, for example, or component-based systems, or even service-oriented architectures, all have some notion that there's an architectural framework or style or commitments that are involved in this sort of thing. And understanding what that architecture is a critical part of getting that technology right. So when we look at what software architecture is today, it's hard to generalize because huge amount of variation. But if you look at organizations today, I think it's fair to say many of them are keenly aware of the importance of architecture. They have job roles called architects, not always with the same definition, but often meaning sort of the key technical person in some project who's going to make these high-level decisions. There are processes now for doing architecture design reviews, books on architecture documentation and guidance. There's a much better understanding today of architecture styles and patterns and basically forms of architecture reuse that typically prescribe a certain set of constraints and vocabulary for a given domain of architecture. There are tools out there, selective tools. I can't say the commercial world has been taken over by good architecture tools, but there certainly are good prototypes and illustrations of architecture tools out there, and they can do fairly interesting things that I'll come back to in a minute. And then there's a lot of things like books, Dick Taylor's book, for example, and others, that have sort of said it's time now we can write all this down, and people can go off and teach courses on this. And so, in that sense, it's a very well-established kind of area. Let me talk about the tools for a minute, because I want to come back to those as one of the enablers here. So when we look at the architecture design tools, they vary all over the map, and I'm thinking of things that go anywhere from UML off to things that are fairly specific to architecture, with maybe very formal notions of what architecture are. But some of the themes that you see if you look broadly at these tools are, one is some recognition of the value of domain-specific architecture development. If you're just in the realm of boxes and lines, PowerPoint is just fine. But once you start narrowing your focus on in-tiered client-server systems or, telemetry processing systems or avionics systems or what have you, you really want to be working in a much more constrained world of design with a specific kind of vocabulary and specific kinds of support for doing that. There are a lot of analysis tools that have been developed. Again, not so many that have been fully commercialized, but they give an indication of what you can do, things that help you determine when you've plugged things together in ways that don't quite work, things that help you evaluate the performance of your system or look for bottlenecks, things that will give you some insight into reliability, things that help you understand security, and so on. All of those ilities that are often the hard things to get right in a design are things that architecture tools are often very good at helping you understand. There's today a lot of interest in multiple views, recognizing that in many cases a system needs to be described from multiple perspectives. And then other kinds of linkage to organizational processes through the tools. So tools to take the architecture description and make them part of the company documentation, ways to use architecture representations in reviews, and ways to manage the evolution of systems through the architecture. Okay, so let's come back now to the end user architecting, and this is where I'm going to try to put together these concepts here and make it specific in terms of what I think that means from a systems design point of view, and how this actually ends up looking very different than our current state of component engineering and execution. Okay, so the approach, end user architecture approach, says what we want to do is we want to provide architecture-like tools to these end users who do these compositions. And the way we're going to do that is we're going to provide an explicit architecture layer between the user and the system, certainly between the user and the execution system, that will formally represent the architecture that they're trying to create, that will allow us to sort of specialize the creation of such systems to their domain, and that provides reasonable user interface to that in the form of appropriate sort of graphical support. So what does this look like? It looks like, if you think of the sort of standard system today, where you have some raw computation primitives here. Let's say, think of services in a service-oriented architecture. You've got an execution platform that's going to allow you to execute these in some form. And then you've got some user interface where you can interact with those or start them up and so on. So what I'm suggesting here is instead what we need at runtime and during development is a architecture layer here that supports or bridges the gap between these users, these end users, and the computations that are going to go on by specializing what's going on in the lower levels to their domain. So let's look at that level for a minute. What goes on here? Well, at the architecture layer, we have a kind of abstraction of the system. Basically, it's going to be a composition of components. And there are a set of things that we can provide once we have that representation, all of which are interesting research or already developed in the architecture community. So we can provide guidance. We can observe, for example, whether someone's particular design maybe violates some standard rules of composition. We can provide analyses. For example, if I run this composition on this huge database, when am I going to expect to get an answer? We can do translation from the output of one component to another. So there's various technologies today for bridging format mismatches that can be automatically inserted in that architecture layer. We can insert automatic monitoring so that when the system runs, we can actually track it, its execution. We can provide code generation in many cases, and in some cases, adaptation mechanisms if we actually have to evolve the system. So we've experimented with this idea as I say, this is sort of an early results here. I can't say that we do all of this and that we have in complete general form, but we've been experimenting at least in 3 domains: the sociocultural analysis, the brain imaging, and now this widget framework for ozone. Okay, so in the case of brain imaging and also sociocultural analysis, it turns out that those actually have a fairly similar flavor to them. They're both fairly transformational, meaning you get a lot of data in one end, and then through a series of various transformations, you get some reports or some kind of visualization of that data. And so what does that suggest? If you're in my class, I ask that question, you say, well, it's a data flow architecture, pipes and filters. It's the kind of architecture style where the components are largely transformational and where you want to hook them together through various sorts of mechanisms that allow the outputs of one transformation to get given to another. And so we can take that intuition about what's going on and put that into an architecture style specialized for this very general class of systems. So the architecture style here that we used is called SCORE. And what we see is we start with some fairly generic notions of elements here that we can then specialize to have both a neuroscience family and SORAS was the name of the sociocultural analysis tools. And then we can actually even specialize that further or provide special things that go into it. So the point here is that we're starting with the notion of defining an architecture style or vocabulary and a set of constraints that go with that domain, and we can actually build a hierarchy of these things as we explore other kinds of domains that are related. The user interface here looks like this, at least our prototype one. This is inspired by Yahoo Pipes. If you've ever seen that, that's an online kind of mashup framework that takes RSS feeds, and it has a very large number of components that you can drag and drop and hook up together and create fairly sophisticated processing pipelines and graphs. So we're using the same GUI framework called WireIt that they use. And the ideas are similar. You can basically take a bunch of these off-the-shelf transformations, plug them together. You have data sinks and sources, And out of that, you get to execute this thing, and the system, as it executes it, will walk you through which of those components are being executed, and you can very rapidly play around with different compositions and different kinds of parameters. But what's going on under the hood is all of the messiness that I showed you earlier is being taken care of automatically. So all the BPL scripts that need to get executed are automatically generated from the architecture layer into the execution platform. Okay, in the neuroscience world is something similar. Again, we're playing with a similar kind of interface here that allows you to plug together these transformations. And again, the implementation is no longer SOA in the way that we saw for the other one. The implementation in this case are these scripts where a set of parameters are plugged in. But also some analyses here. So in this case, there are a certain set of sanity checks that you need to make on one of these computational pipelines here in brain imaging. So in this case, it turns out you need an alignment step before you do this temporal filtering. The system noticed that there wasn't there and gave some guidance so that someone plugging this together would know that they hadn't quite put it together right. And so there they have put it in. Going back to the first system, the actual implementation of this, which is available for anyone to run, looks like this. There's a sort of standard SOA infrastructure there where a bunch of tools like the ones developed at CMU and other places are wrapped and then presented through typical, in this case, Apache web service infrastructure, so with a registry and an orchestration engine and so on. The interesting stuff goes on at that next level, the green level, where we have all of the higher level componentry represented there and other kinds of services. So here's the interface I showed you earlier. That goes in here and that hooks up to those things. So in this case, that middle architecture layer is providing sociocultural analysis. In the case of brain imaging, it's doing something very different. Okay, so there's a few details about that implementation, which we've taken probably farther than the other ones. There's about 120 services that use 10 standalone tools built at about 6 different organizations. And it's being used today by certain parts of the U.S. intelligence community. Okay, so I'm going to transition a little bit now. What I've been trying to do is to argue that by inserting or insinuating architecture into the thinking about what people do, we can get some real benefits, and that many of the things that we learn from architecture carry over into this world. But I think it's also worth sort of turning it around and saying, are there insights that we get from doing this kind of thing about what architecture environments should be providing? Things, at least in my experience, we didn't have in the kind of tools we were building. So I'll just mention a couple of those. This is more, I think, for people who are interested in doing architecture research here, but maybe more generally. Okay, so the first thing was, most of these systems have a huge number of components out there. And you definitely need a way for users to have access to those, to know what they do, to organize them in very useful ways, to search for them, and to find out information about it. Who produced that component and where has it been used, okay? So there's a lot having to do not just with the style or the organization, but the actual instances of reusable parts. Okay, so that was something that we had to tackle, and I think it's an interesting question of how do you do that in general? How do you create ontologies of components and the right kind of information that's appropriate for that domain? As I said, another big deal here is mismatch. Often these things don't work together. The formats aren't quite lined up. And the question is, often you'll end up with a very large number of potential data transformers. You'd like to ideally plug them in, but you need some kind of calculus of data mismatch repair to help you. So the whole idea of automating mismatch repair, I think, is an interesting one. Another one that's important here is how do you package up these complex compositions in a way that can then be shipped off to someone else or used fairly simply by exposing a couple parameters that can then be instantiated. Some ideas about that, but that's a little bit open. And then finally, and a really important one that I think almost all of these fields have, is this whole question of pedigree, provenance, credibility. So I just did this analysis. I get this astounding result out, and I can't quite believe it. How do I know where that came from? What contributed to that specific result? Where along the chain of reasoning did that particular thing emerge? And this is something I think is kind of interesting, in part because you can do a certain amount architecturally. Since we're compiling this into an execution, we can easily monitor what's going on. But in many cases, the relationships between inputs and outputs are very specific to the tool that did the transformation or the calculation. And so you really need to get its help in understanding some of these things. So I think this whole idea of reasoning about the outputs based on how you calculated them is something that's really, we've seen many times here. And I don't have a general solution for that, but I think it's an interesting problem to look at. So I'm going to finish up in the next 5 or so minutes by talking about something else that we learned here. Most of us here are probably technologists. We're most comfortable when we're off building things and coming up with new creative ways to do software development or things that are related to that. Unfortunately, something that I guess I learned the hard way through some of these projects here was that good technology isn't always enough. That often, the context that you deploy it in is going to determine whether that technology is successful or not. Now that may just seem totally obvious. Clearly when we design systems, we need to be aware of the requirements and the stakeholders and all of that. But believe me, a lot of us, I'm sure, have gone off and built systems that are technologically beautiful, only to discover that the organization that we're putting them in, there's no incentive for anyone to use this, even though if there were, it would take off. Or that there are regulatory concerns about this tool because we didn't know about this particular clause in the contract and so on. That there are these things that occur that make technology less useful than you hope. So I'm starting to get interested personally in this and working with Jim Herv's lab, who some of you do research with, on a somewhat more systematic understanding of this, that today is starting to be called socio-technical ecosystems. And the idea there is that, when we think about the technology we produce, we're producing it to work in some social, cultural, governmental, economic context. And then we need to think about that context in a way that gives it a first-class position in terms of the design. Some of this sort of traces back to kind of standard sort of requirements engineering, but I think some of it also suggests something a little bit more. So what's involved? Well, obviously we need to know what kinds of roles of stakeholders are in this ecosystem. We also need to understand incentive systems. What is it that makes someone willing to do something we want them to do, like buy our product or contribute an app? Why would they do this? We need to understand the organizational, governmental, economic, social structures. So there are an awful lot of things like that that are often relevant to how these things are going to work. And then, of course, the architecture, the technical part, let's say a platform of some sort. Just to illustrate this, with a probably familiar example is when we think about, the structure of the computer industry. This is from Economist, a fairly famous paper that looked at, how the computer industry evolved from the early 90s on. And the old days were largely characterized by ecosystems dominated by a few companies, each of which did everything for themselves. So they created the hardware, they created the operating system, they created the applications, they did their own marketing and their own service. Everything was stovepiped within that organization, whether it was IBM or many of these other places that probably no one even recognizes anymore. Well, what happened? What happened was the ecosystem completely changed with Windows and other kinds of platforms that gave more of a layered world here in which you could have a much richer set of supply chains and relationships. So now, in this world, we have many, many more different roles. It's not just IBM doing its things with its employees. We've got separate kind of marketing distribution channels from the people who are writing the applications, from the people who are creating the processors and so on. So the world suddenly became much, much more interesting from an ecosystem perspective. And today, you can't think about doing anything without worrying about these multiple layers. Whereas in this world, it was very simple. How do we get all our employees to contribute to our particular product? So I think when we start looking forward into how technology and its environment work, we need to think about these ecosystems explicitly. And again, I think we have lots of interesting examples about us now. When you think, for example, about iPhone as compared to Android, they are in some sense each creating their own ecosystems with different commitments in terms of their architecture, but also engendering different kinds of roles. So, the app market in Apple is somewhat different than let's say, the use of Android in mobile systems, for which people have to come up a level or so before they get the kind of functionality they need. So, thinking about socio-technical ecosystems as first-class issues in our design, I think becomes an important thing. So if we look at some of them, well, we have some classical ones, sort of the single product-oriented socio-technical ecosystem, basically, I build it, you buy it kind of world. That's sort of simplistic, but, and they're still out there. But if we think about now something like a product line socio-technical ecosystem, people have observed, from a technical perspective, a product line can revolutionize the development of systems in your organization. Totally revolutionize it in terms of the cost. And yet, the world is littered with failures of product lines. Why? Well, because often the organization is not suitably set up to support the product line. They don't have anyone to maintain the product line. They don't have any way to govern whether some instantiation of it is consistent with the product line, and so on and so forth. So it's not the technology, often it's the organization in which it's placed. So if you go into a product line development and you're not thinking about the organizational changes that have to get made or appropriateness, it's not going to work. Service-oriented socio-technical ecosystems. So today, SOAs are fairly popular, but they raise the whole question, where do the services come from? How do we govern them, and so on? And those questions have to get answered. How do you get paid for the services that are being used? Platform STEs. So again, things like iPhone and Apple and so on now become sort of increasingly part of the landscape, because companies are realizing that the way to really leverage a product is not to build it themselves, or not to build all of it, but to create the platform where gazillions of other programmers will contribute to it. Okay, so now we have a much more complicated and complex ecosystem. So coming back now, full circle to the end user architects, you have to ask, well, okay, if we want to have these communities of domain experts like brain imaging researchers, and we want to have this platform where there are all these tools that they can use and so on, what do we need? And you need people to actually be developing the tools and services. You need to have someone who's supporting and maintaining the platform. You need someone to govern who can put what services and components into the system. Of course, you need the end users who are going to use it. And you have to worry about the other external forces. Are there government regulations? So if you're doing e-health, what do you need to know about privacy or anonymization? If you're doing economic benefits, how do you decide how much to charge? Do you charge for the apps, or do you charge for the platform? Do you charge for both? How do you balance that? Other kinds of social constraints. Is it going to fit in with the nature of the way the community of people using this will interact? So I have to say, we learned the hard way that if you don't think about these things, it doesn't work. And I'll mention a couple of the things that we ran into. In the SORAS system, which was the one for sociocultural analysis, we were the platform developer, And the tool service developers were a very large number of researchers out there, mostly in social science. The end users were the analysts. And at this point, our governance body was our lab. In other words, we were getting things to stick in this system. As I said, we ended up with about 120 services. The problem was it never took off, and there may be many reasons. I tend to think it's not the technology, but what we realized, for example, was the incentive systems weren't there. So, for example, you're a sociologist, and you just came up with this really whizzy new way of analyzing cultural data to learn about trends of religious evolution, whatever. Okay, you just come up with that. You just published a paper on this. Do you want to give your tool that just did this up to the community so everyone else can publish the same paper, same kind of paper? No. In fact, there are huge disincentives to kind of share the models and the tools in this particular community. Okay, so recognizing that up front, had we done that, would have said, well, wait a minute. Either we don't do this, or we have to find a way to counterbalance that. For example, funding agencies that say, you know, if you're going to do this, you better make it available in this platform. Government regulation. So for us, we went into this project and we were very clear. We were going to use open source infrastructure. We wanted to make it, you know, very open and clearly usable, extensible by people. And once it started being successful, the DoD supporters said, okay, well, now we want to transition this into real world. Of course, we have to certify all this stuff. Certify? What is certify? Well, certify is this 10-year process where people go through picking away at the thing and making sure that it's not going to do something, you know, bad to mobile phones in Afghanistan. It turns out, had we known this going into it, we probably would have picked a whole different suite of technologies that had already been pre-certified by the government that we could have probably used just as well, but we didn't know that. And so we made some bad choices. As a result, we were told, you know, this is really nice as a research prototype, but someone else is going to have to rebuild it if we want to actually use it. And so on. There are a variety of things like that. And my only point is that, you know, I think this is really a terrific idea when we go into it of providing these platforms for end users to do composition. And it takes architecture in many ways out of the very sort of narrow, sort of religious, small community of gurus who do architecture out to the masses. And I think that's great. But we really need to think about the harder problem of these ecosystems. So let me conclude. So end users today, certain classes of them, are creating fairly complex systems using compositions and, I would argue, architectural abstractions. And that we can take these ideas, we can provide frameworks for doing this design, and we can leverage a lot of what we know about architecture tools, styles, reuse, analysis, and so on. There are some open research issues, I think, that come back the other direction. You know, how do we deal with large repositories of components? How do we deal with provenance, and so on? And finally, that, you know, as we think about reaching out to these communities, which are now very complex, you know, the world of brain imagers has their own set of rules and conventions about how they interact. If we ignore those cultural, economic, social influences, you know, then we can very well end up producing something that's just not of any use at all in those communities. And so we need to somehow find a way to bring those concerns up front as we're thinking this through. So just to finish up here, this is joint work with a number of people, graduate students, colleagues, some people in Portugal, also in Mexico. For the record, there are a few publications here if you're interested in. And a bunch of tools. I mentioned there are some things out there that are good examples of what we're talking about here. There's a list of those. So with that, let me stop, and thank you for your attention, and I'll take questions.
Certainly it's time for questions. So
a couple of times in your lecture, thank you, by the way, you said things that were somewhat negative, but perhaps rightly so, about developers and organizations. And it sounds like there's the end user developer, but it sounds like there's also sort of this bad developer that takes years and years to develop things and things never work. So is there a reason we're kind of going away from, okay, let's have a team of developers at our company to make this happen, to this, hey, we can just architect it, let our end users do that? Has that group of developers become particularly ineffective recently, or is that?
Well, I think we need to be a little more nuanced about that. So the question is, what about these developers that I seem to be maligning? I think, there are developers of the tools that ultimately get used and presented to these communities. And those guys are often know very well what they're doing. That's what they're doing. They're developing tools, and they're very good at it. So those aren't the ones I'm talking about. What I'm talking about is you're a researcher in brain imaging. You can't figure out how to make these parameters work, so you hire some undergraduate as an intern to come in for the summer and glue this thing together. Okay. That's what tends to happen. It's sort of, this is not my job, I don't want to do with it, make it work, and let's get on with it. Okay, so you end up with really crufty bad code that no one else can use. If you have to change it, you can't, and so on. So that's the culture that we see today. Now, it might very well be that there's a reasonable job opportunity for people who make that their specialization, who really say, I work in brain imaging composition, I can go and do things for you. But today we don't see that very much. Dick?
So the question has to do with what kind of model do you present to people in the user communities for them to compose these things. And the example you showed was based upon Yahoo Pipes. But it didn't sound like you were really saying that you thought that was the appropriate way to go or the best way to go.
That's right.
What are your thoughts about to what extent does that notation need to be domain specific? Right.
Yeah, that's a really good observation. And I left off part of the story here. At least in the context of this system, what happened was there were a bunch of third parties that said, we can take these workflows and give a much better interface than those, but much more narrow. So for example, there was a company, I forget their name right now, they are interested in belief network analysis, so a very specialized facet of this whole field. And they say, we can give you a belief network front end that makes it extremely easy. You push these buttons and it all happens, and the workflow all happens underneath. And I think ultimately that's the right answer, that you really do need people who are specialists in the user interface world for those communities. So I kind of view this as a transitional step. I think that sort of, at least it exposes it at a much higher level than people or the other things they're working with. So it's a step in the right direction, but I wouldn't for a minute think that that's the final say.
But you discovered, it sounded like serendipitously, that the structures of the tools in the intelligence analysis world were similar to that in the brain imaging.
Right.
Yeah. Is there any reason to believe that kind of an appropriate model for end users to use for composition might similarly be the same or close across domains? In other words, how domain specific do you think that top level notation needs to be?
It's a really good question, and I think there's a balance here. So in this particular system, I think they went the wrong way, the other way. So in this one, you've got these widgets that you stick on the screen there. And you look at that, it looks very whizzy and cute, because all of this cool sort of interactive stuff all pub-subbing to itself. But if you said, well, who actually communicates with whom here? And if I send a message, am I sure this can actually get to this other thing? You can't figure that out. You have to go into the code and start looking at what they actually are doing there. So here they've taken something which I think is too high level. It's a very simple composition framework, but they haven't exposed enough of the architectural glue so that you can answer questions that you might want to ask. Okay, so I think it's a good question. It's an open one. I don't know. But certainly there's a balance here of sort of ease of use, domain specificity, but also when you need it to expose what's going on so that you can answer the right questions. So I don't have a great answer to that, except I think it's a hard problem and often very domain specific. Yeah.
Can you speak a little more to the social problems you mentioned at the very end of your talk? How do you get these highly disincentivized researchers to participate other than just exerting some sort of grant pressure on them?
Well, it's a great question, but unless we start asking it, we probably won't come up with answers. That's a glib answer. But let me give you an example of something, for instance, that I wanted to experiment with before the grant ran out and never had a chance to do it. Suppose that whenever you produced a result, it was annotated with tools that created that. And that you were required, when you use this thing, if you actually use that result in any paper, to credit and use that bibliographic citation in your work. Okay. Now we're introducing part of the incentive system these guys really do have, which is credit for their stuff, into the tools that actually help promote that. So now someone says, yeah, if everyone's using my tool to create their papers, I'm going to get a lot of publicity, up my citation count, improve my chances for tenure, and blah, blah, blah. So I don't know the answer completely, but I think there are creative ways like that. Once we recognize that this is going to be a problem, that we can start doing something about it.
Yeah, I also wanted to ask about the social. When you talked about the sustainable socio-technical ecosystems, I was thinking, well, actually, if you take the legal and government side of it, that's actually a pretty unstable field. I mean, privacy is changing all the time, security is changing all the time. And I was wondering how you can, how do you understand sustainability with respect to the constant change that's going on in a number of these fields that you're talking about, and can you still architect for that?
Right. I mean, I think this fits into a bigger problem that in the technical world is sort of been framed in terms of evolution. And it happens, technically, I've got something that uses technology today, but tomorrow this is cloud computing, and how do I get from here to there? So that's generally a concern, and I think people haven't sort of brought in the kind of question you're asking, which is we have to also worry about what's happening around it. If that changes substantially, then that may mean some changes to what we're doing technically too. I think it is really an issue, and part of planning, I think, a lot of what software engineers think about is planning for change. In fact, if you go back to the origins of modularization and all that, it's all about how do I limit the impact of some change. Well, we know from experience that's not a great strategy unless you have some idea what kind of change might be there, because you can't make things arbitrarily changeable. So it strikes me that by bringing that question in up front and say, well, look, I understand the government may be adding this extra tax on blah, blah, blahs. What would we do now, given that might come about, to engineer things so we can deal with it? So I think a lot of the same lessons apply, but we know so little, in my view, about these socio-technical systems. How to represent them, how to know if we have enough complete information about them, how do we know what are the first order impact relationships and second order ones. So I'm actually personally interested in this. I'm working with Jim Herbsleb on this. We offered a course last spring in socio-technical ecosystems, and I'd be happy to share with you, the reading list we had for that. But it was basically trying to pull together everything we could think of that might relate to this field, from biology to economic systems to platform design, so on, to try to understand, what is this field? How can we wrap it up in a way that people who are working with technology can get their heads around what's important? So I think this is an interesting opportunity here, something I'd love to be doing more of.
It seems like there are two groups of people, a large group and a small group, the large group being the users of one of these user-oriented architectures.
Yeah.
The small group being the ones who implement it on behalf of the large group.
Yes.
So, for instance, in your brain imaging example, the thing actually has some knowledge of the semantics of the domain. It knows, well, this particular transformation was omitted. Mm-hmm. And so I was kind of wondering what experience you guys have had in terms of the notations to express that semantics? And it's sort of a question oriented toward the small group, the implementers of division. What notations have you found convenient to express those semantics when you built the systems?
Yes, it's a great question. We've played around a lot with sort of formal representation of architecture constraints, which can be done in terms of just sort of first order logical descriptions over the architecture. But those only go a certain distance there. What we actually did in this case was we used machine learning to look at a whole large number of these workflows and single out what were typical kinds of orderings that we saw, and use that as a kind of advisor here. So that's a completely different kind of thing. The one which is I can write it down because it's a constraint, I have no logic, I can do it. The other one is I don't know what it is, but maybe I can figure it out by looking at a number. So I think there is no one answer to that. It depends a lot on what's out there. But I do think that in many cases, all along we've known that there are good architects and not such good architects, and the good architects often have in their heads rules of thumb and ways of doing things. And sometimes the problem is how do you get it out of their heads into a form that other people can use.
Thanks for a really interesting talk. I want to ask a little bit more about, I guess, the feedback loops that come back to the users of the systems. And when you're doing this kind of abstraction, where you are creating this sort of simpler language to describe what's going on underneath.
Right.
But a lot of times these are actually really complicated analyses that turn on minutia.
Yeah.
And as an example, I've worked with some people in genomics and bioinformatics where, using a workflow system to run on top of a cluster, depending on which machines happen to be running at that time, depending on how much memory was on them, you would run exactly the same workflow and get the same different answers out of the system.
Different answers because
of the amount of memory and some of the sort of, deep in the code kinds of shortcuts they were taking to make these problems actually, computationally doable.
Right.
And it took 15 people in a week to figure out what was going on.
Right.
And I'm wondering, how do you, when you've got those tight links that are actually through that stack, how do you get that feedback back to users?
Right. Okay. So it's a great question, and I didn't talk too much about that, but I think there's a whole very interesting question of how you relate the architectures to the execution platforms, and what kinds of information or knowledge about that is useful to the user. And also to what extent you can automate some of those things so you don't get that weird stuff. So for example, in the SORAS world, we automatically ship the data over to the computation because we found that typically improves the performance quite a bit. So we do a certain amount under the hood that the user would otherwise have to do themselves, just because we know that's a good thing to do. So part of it, I think, is a question of recognizing, what are good and bad ways to actually do that deployment, building them in. And the other ones, I think, you just have to be able to know these are significant to the end user, and therefore I need to make them aware of those things, which means mapping back into their vocabulary in some form. But I think that's a tremendous opportunity here because when we control the relationship between those two things, we can do that analysis. And they're not just working in the dark. We have the knowledge to actually give that feedback, or at least the placeholder to put it. So I think there's a great potential there.
Actually, my question is kind of related to the previous question. The kind of systems that you talked about mostly deal with large amount of data, millions of images, and mining those images, processing those data is very time consuming. And also in your approach, you are adding another layer to the architecture that could also affect the the performance of the system. Did you have done any study that, for example, try to see if the end users are confident with your new system based on the performance and or not? Because sometimes if the performance is very low, they maybe like to use the traditional method and hire someone to code something and integrate the system by manually, not by your proposed approach.
Right, right. I mean, I think there's a little like the old arguments about high-level programming languages people used to have. Someone says, I really need assembly language to get the performance out of that, and that may be true, but it's probably not true for most people. But the compiler can do at least a good job as most people. And I think we see the same thing here. A lot of the sort of performance tweaks that a good person actually, let's say, writing the SOA script would do, we can actually build into our tools. Now, that doesn't mean that it's for free, and there is a certain amount of overhead, but compared to the other kinds of processing, it's pretty minimal. So, for example, we build in automated instrumentation so that as the workflow is executing, we can tell the user where we are in that. Okay, and yeah, that's going to be a little overhead, but compared to the transformational time that most of these things take, it's trivial. So we haven't seen in our particular domains a whole lot of pushback for overhead there. In fact, most people have been glad that we've been doing it because we can usually do a better job than they can.
To what extent did you use domain-specific users for validating your development activities, say in the different projects?
Right, right. Well,
did you notice any differences?
Yeah. So the community where we did the socio-cultural analysis was one that we actually had a lot of feedback. So we had a number of community meetings over a period of 3 years where we brought in 20 to 30 people in a variety of roles, both analysts, government people, tool developers. And we presented them with our steps along the way. We actually had to change a lot of things because of that. And there's some other stories, maybe take offline, I can tell you some of those, but I think it is critical, right? You know, so we tend to come from the technology community and we're actually trying to address some other community that isn't. We really need help to get that right. So I wouldn't want to ever underestimate that effort. In the brain imaging, let's see, we're working with a couple people who do research in brain imaging. So we don't have a huge community there, but we're getting some feedback at least from people who actually do that. And they're just so thrilled they don't have to provide all those parameters. That anything that we give them is viewed as positive. So anyway, but I definitely agree with you. You have to really get someone familiar with the domain to help out. I guess last one?
Last one.
So say you want to do this for a new domain, so define the same thing for a new domain. So which parts of the socio-technical ecosystem would be involved kind of in defining this domain-specific style and things like that to make it happen?
I don't have the answer to that at the moment, because that's what I'm trying to figure out apart from these examples. But I think what you do is you go and you say, in order for this to be successful, what are the various roles in the community that are going to have to be played by someone? What do I want each of those roles to do? And then what's the incentive for them to do that? And that's going to vary from domain to domain. I think all of them tend to have the same, at least certain essential ingredients, which are the ones I had here. Find it. Okay, so you need to ask, who are the stakeholders, typical kind of thing. You have to ask what's their incentive system for them to do that. You have to ask, are there any regulatory, governmental, or other kinds of forces going on here? And then you have to make some decisions in your architecture about how you're going to distribute different activities and roles. So for example, if you picture people adding components to your system, is it in the style of Mac apps, which are very highly constrained, or is it in the style of applications that run on Android, which is much more open? So you have to start making those decisions in that space. But I don't have a checklist. I wish I did. I wish one could say, this kind of system, here's the ecosystem, here's the things you should really look at. I think that's an emerging field that should be defined.
All right, so I want to thank David one more time for the talk.